Okay, so welcome to the second LOPSTR session of today. We have 3 papers, 2 long papers and 1 short paper. The first one is about Predicate Anti-unification in Constraint Logic Programming by Gonzague, Yernaux, and Vanhoof. And the presenter is Gonzague. Please, Gonzague.
Yeah, thank you. So hello everyone, I'm Gonzague, and in this work we've tried to define to come up with a first definition and formalization of what could be called predicate anti-unification. Anti-unification itself is well known. It's defined as the fact of computing so-called most specific generalizations, or MSGs, of program objects. So the program objects can be terms, atoms, literals, goals, but it hasn't yet been defined for predicates and clauses. And an example of anti-unification is given here, where we have 2 atoms, and as you can see, the atoms share some common structure. There are some functors appearing in them, some terms that are the same, but some parts are different. And the result of anti-unifying these, which is in fact the dual operation of unification, is a new atom that's more general than the 2 input atoms. So as you can see here, we have a new atom which introduces variables, and the variables in fact are what allows this new atom to be more general than both the input atoms. So for example, here I have an A in the first atom and a B in the second one, so I put a variable to show that there's some part here that's in fact different. So the generalization can be seen as a common template for the 2 input atoms. And the common uses of anti-unification are, for example, in inductive logic programming, where the whole goal is to learn new, more general rules starting from base facts. So you can anti-unify the facts and try to get some more general rule in this setting, but also in partial deduction, where it can be used to control some searches, in bug detection, code compression also, and the last example here, semantic clone detection, is the context that interests us, because we're leading some research in semantic clone detection in logic programs, and anti-unification in fact represents, by representing the common structure of different program objects, it can in fact represent also what's common between the atoms. So it can represent also, it's interesting because although it's a syntactic operation, it can represent some things at the semantic level too. The generality introduced is also a semantic one. So in practice, anti-unification has been well studied for ordered structures, such as terms. You know, the terms are ordered in the way that, in the sense that there are sequences. And in that particular setting, we have, for example, subsumption, which is well known, and which can be carried out in linear time. And then you have more complicated settings, for example, when you consider unordered groups or sets. For example, goals, when you consider the purely declarative logic programming, where the bodies of the clauses are composed of sets of literals rather than sequences of literals as in Prolog, then the problem directly becomes NP-hard, and it's a whole other story. Anti-unification techniques exist also for other structures, such as hedges, lambda functions, or even in functional programming for regular functions. But it does not yet exist for logical clauses and hence for predicates. And as I said before, it's necessary in our work, where in fact the clone detection process is steered by the fact that we consider the MSG, or the most specific generalization of two predicates, to be given, because thanks to this MSG, we can decide in our search process, we can decide how could we syntactically transform the input predicates so as to make the definitions closer to one another. And the generalization of both predicates actually has and harbors that specific information, but it hasn't yet been defined before. However, some related problems have been studied in the literature. Some have already tried to quantify the syntactic closeness of logic clauses and even whole inductive logic programming programs. Some others have tried to mimic analogical thinking, still in the context of inductive logic programming and machine learning, by using so-called higher order anti-unification, where you can also variabilize in the generalization process. You can also variabilize the predicate names, for example. And then even closer to our own work, some authors have studied the search for a blueprint of the algorithmic core of functions, which is not that far away from our own goal to detect semantic clones. And in that context, it's for functions, and of course we are more interested in the predicate side, but the idea stays the same. So anti-unification is known to be useful in fact, to have semantic applications, but as I said a few times before, we haven't got yet an algorithm for two input predicates to actually compute their anti-unification. So first, let us take a step back and consider the formalism which we'll be using here. And let us consider this example where we have two predicates, take and next sum. The first predicate, take, well, it computes simply in its third argument. A call to take succeeds when its third argument represent the first elements of the list in second argument. And the third argument is thus a sublist of the second argument, but restricted to the E, where E is the first parameter here, first elements. And as you can see, the body of the last clause here is in fact a set. So we have written the atoms, the literals, in a certain order, but in fact it doesn't, since we consider the fully declarative semantics, this does not, there is no real order here. And in fact, we also, as we're really interested in the theoretical results here, we also consider the different clauses to not be ordered. So a predicate definition is a set of clauses too. This will be important later on. And then you have the predicate next sum there, which computes in its last argument the negative sum, so simply minus and then the sum of the I first elements of its first argument. So although these two predicates, of course, they do different things. One of them extracts elements from a list, and the other one computes the sum, the negative sum of the first E elements of a list. There is some common functionality here, and that is the fact that we crawl through a list and we make an operation element after another, and we do these operations until for the first X elements here, E or I elements. So we would like our algorithm, our predicate anti-unification algorithm, to express this, to be able to compute a generalization of these two predicates that expresses the common functionality here. And as for syntax, we say that the predicates that allow to compare elements, numeric elements, are constraint predicates. So we have constraint literals that are built upon constraint predicates. And then we have user-defined predicates, in our example, take and next sum, which are both recursive. And so we say that the literals built upon these user-defined predicates are atomic literals. But in fact, as you can see in the title, we've put constraints between brackets because here the fact that we use constraints or not is not really relevant. We're simply considering literals. So when we're speaking about literals, we're considering either atoms or constraints. Both are considered literals. And then we have, as usual, functors, which allow to build terms. So in our example, for example, E minus 1 is a term built on the functor minus, and the terms are used as the arguments of the literals. So, as I said before, anti-unification is well known for tree structures or sequences. So let us start by defining it formally. So given three terms or three literals, G1, G2, and G, we say that G is a common generalization of G1 and G2 if there exists two substitutions such that when I apply the first substitution on G, I get exactly G1, and when I apply the second substitution on G, I get exactly G2. So this is the usual definition of generalization and common generalization, and it's not unlike what we saw in the previous presentation with the generality of substitutions. And as usual, we consider a substitution to be a mapping from variable to terms. So here we have a quick example where we can see this term here, based on the functor f, has two variables, and it can be seen as a generalization of both the terms that are there below, because we can find the mapping from x and y onto 1 and h, and that's one substitution, but also onto S4 and KL0, and that's the second substitution. So fxy is a common generalization of these two terms here in the example, but it could in fact be literals. That's why we regrouped here the cases for terms and literals, because they are in fact very similar. Now having such common generalization is really fine, but as I said before, anti-unification is about finding the most specific generalization, because just any generalization is not really relevant. Here in the example, well, this can be seen as the best common generalization of both, but I could also simply have put a variable there, and that would have been a correct common generalization of the two terms. However, it wouldn't arguably be as specific, as interesting. So to stay parametric on that regard, we defined a quality function as being simply a function that associates a real value to any program object. And by program object, we mean terms, atoms, literals, goals, clauses, and predicates. So a quality function allows to say, okay, this is what we will consider a better generalization. To go back to our example before here, if I had the functor 1 that was here in the first term, but also in the second, then the generalization having f of 1 and then y would be a better generalization, because it's more specific. But to capture that, some might also consider, for example, that this generalization is maximal, because it's composed of as many terms, it represents as much common structure as possible. But this exact definition of what it means to have common structure is in fact very variable on the context. So this is our parameter omega here, which is a quality function. And for such a given quality function, we say simply that a common generalization is omega maximal is an omega mg if and only if it is maximal omega y. So if there doesn't exist another common generalization that has a higher quality. But remember that the quality could be, in fact, anything, depending on the application, as long as it's a real value function. So here we have an example of a useful quality function that we'll consider in the remainder of the presentation. So this quality function is based on the notion of norm, and a norm in terms is something that for a given term gives the size of the term. In this case, we define the size of a term as being the cardinality of the multiset of terms that appear in it. So if a term has a lot of imbricated functors, then it has a higher norm. And based on this norm, we can define the quality function, which we'll call tau here, which is one instance of the omega function that we discussed before. And this quality function tau, for a term, associates its norm. For a non-empty literal, it's considered 1, and that 1 will be useful later on, plus simply the sum of the quality of the imbricated terms in the arguments of the literal. And to a goal, a clause or a predicate, simply the sum of the qualities of their constitutive parts. So that's a straightforward notion of quality function that we'll use here in our abstraction later on. So given that quality function now, how can we compute tau mg's, which are, remember, maximal generalization relative to tau for terms and literals? Well, first, we'll consider that we have some function phi that computes, that outputs a new variable name for any two terms that it has as arguments. This is simply a helper function that will help us define the rest of the things. Now we can define this anti-unification function that for two terms or literals, remember this could be literals, it outputs either the empty atom true if both literals are these are literals but not based on the same on the same predicate name, sorry. So in that case, we simply say, well, it's true, it's the empty literal, which has quality of 0. If, however, the two symbols are the same and have the same arity, then we can recursively call the anti-unification function in each of the arguments. And whenever we have two different terms, then that's the third case there. If we have two different terms that we need to anti-unify, but these terms don't have the same arity, the functors don't have the same arity, or the terms are based on another functor or different functors, then we introduce a new variable that's specific for these two terms. And it's easy to see that this anti-unification, computing the tau maximal generalization of two terms or literals, can be computed in linear time.
But that will be the most specific one.
That will be the most specific.
Because the same term could appear several places in the subterms, and you want to take account of that.
If the same terms appears multiple times, then it will be handled by the recursive cases there, because if you have twice the same terms that are anti-unified with one another, it will be the same variable that will represent them. So this is considered to be, well, most specific in that regard. But
It's handled by the phi.
yeah, it's handled by the phi. And this is actually an interesting question, because indeed the tau function defines what we will call most specific generalizations. And in this work, we call them tau maximal generalizations, because we consider a quality function, whereas in the literature, often one quality function is given and is considered to, in fact, we don't even speak about quality functions, we simply say that's most specific. Here, we keep it parametric, and but to actually give an example of a concrete anti-unification operator, well, we need to instantiate omega, and here we use tau. So now we can define the anti-unification of other structures than atoms and literals, for example, goals, and this is straightforward. We say that a goal G is a generalization of G prime when there exists a substitution such that applied on G, well, we get a subset of G prime, because remember, goals are sets. And then we can again construct the notion of common generalization. A common generalization is simply for two goals, a goal that's more general than both these goals. That's a generalization of both these goals. Now let's go further and try to generalize clauses. When we have two clauses, we say that the first clause here, C, is more general, or is a generalization of the second clause there, C prime, when it has less arguments, or the same number of arguments. There exists a substitution sigma, so this is usual, such that the goal is a generalization of the goal of C prime. So this is not new. What's new here is that we also need an injective argument mapping, which is a function that maps the arguments of the first clause, appearing in the head of the first clause, to the arguments of the other. The idea behind that is that when you have two predicates, maybe there are corresponding arguments. So in our example, for example, of course, next sum and take, we could see some correspondence of the arguments, but maybe we need to swap some arguments to see that correspondence. So we need to consider the order to not be fixed. So that's the idea behind that argument mapping. And of course, such that each of these terms, which are in the head of C, is itself a generalization of the corresponding term in the head of C prime. So this is what it means for a clause to be more general than another. So here, as you can see, we don't consider tau anymore. We're really speaking in a general sense. So as a simple example, the first clause here can be seen as a generalization of the second one, because although they have different names, this is not important here. It doesn't play a role in the definition. We can see that we can see a mapping from the first argument of P and the second argument of Q, and also going from the second argument of P on the first argument of Q, such that in fact we have a correspondence, and then still considering the same mappings, the same substitution, we can map also the literal here appearing in the body. So we are in the definition. C is, the first clause is more general than the other. Now let's get one step even higher and go to predicates. If I have two predicates, in fact, I would need the clauses to be more general than the clauses of P to be more general than those of Q. Yes, but again, remember that the clauses are not ordered. So they are themselves in a set. So we say that P is more general than Q if it has less arguments. It has also less clauses, fewer clauses. There exists still an argument mapping. Remember the relations between the arguments of P and the arguments of Q. But now we also need a close mapping between the clauses of P and mapping those on the clauses of Q, such that simply for each of the clauses in the domain of this gamma mapping, the clause in P is more general than the corresponding clause in Q. But always with the same involved argument mapping alpha, because the arguments could be in a different order in the predicates, but for all the clauses, it's the same order that needs to be considered. We can permute them, but always for all the clauses the same. And quite naturally, we can now define a common generalization of two predicates with respect to an argument mapping alpha and clause mapping gamma as a simpler predicate where each of the clause appearing in the predicate is more general than both the input clauses, with maybe different argument mappings, but such that these two argument mappings are coherent with one another. I won't go into the details here, but this simply says that the two argument mappings, in fact, are well defined so that the common generalization is a common generalization for both. Now let's go to our main contribution, which is an algorithm to anti-unify predicates. So let's get back to our example with take and next sum. And the idea is that we will have to build these alpha and gamma that allow to show that, to compute a common generalization. How can we do that? Well, what we introduced in the paper is an algorithm that does these computations in a greedy way. So first, we build a matrix containing the quality of, containing in each cell the quality of anti-unifying each pair of arguments. So we have a matrix corresponding to all the arguments, and we see for each pair of them how much quality it yields tau-wise to anti-unify them. And then we have a similar matrix for literals, because we also need to map the literals on one another. And then we greedily select the cells to obtain a high overall quality, while still allowing for some backtracking on the maximal cells. If we have, for example, two cells that are maximal quality-wise with a value of 10, for example, we'll put those two cells on a stack and explore the two possibilities. So the matrix is like this for the example, and this is the matrix on the level of the arguments. So as you can see, in fact, it could be more clear this way, because as you can see, we have the arguments on the left. These are the arguments of take, but of all the clauses, and on the top there, we have the arguments of next sum of all the clauses too. And then for each couple of those, in each cell, we put the quality, tau-wise, of anti-unifying this pair of arguments together. But in fact, consider, for example, that we select the underlined element there. What's interesting here is that when we select this element, we won't be able, we actually constrain the second argument of take to be mapped on the first argument of next sum, and we also constrain the third clause of take to be mapped on the third clause of next sum. So this is important because it will eliminate, in fact, a whole range of cells in the matrix. It will eliminate the cells involving only one of the selected clauses and those involving only one of the selected argument positions. So we can do the same for the literals, and the only relevant literals here are in the third clauses to have this matrix. And the idea of the algorithm is to greedily select the best possible cells. So in this example, we'll take the cell with value 3 here. And this will actually constrain some clauses to be mapped together. So since we mapped the third clauses together, we know that we consider this green rectangle here. And so we eliminate these two rectangles and these two. And we also eliminate all the cells where the second argument of take is mapped onto another than the first argument of next sum. And by greedily selecting those maximal cells at each iteration, we in fact can build a pretty good approximation of the generalization of the anti-unification. And why do we need an approximation here? Well, it's because trying to get all the possible possibilities, all the argument mappings and the close mappings that could yield the best generalization in an exhaustive way, well, that would be, of course, problematic on a complexity level. So here, we really try to approximate this. And in the second matrix, we also have that when we select a cell, we also eliminate a whole range of other cells. I won't go into the details of the algorithm, and simply observe that the matrices are typically sparse. As we have seen in the example, there are a lot of zeros, in fact, in the matrices. So this allows the algorithm to run fairly quickly, and that we compute both mappings simultaneously. But we could imagine a version of the algorithm that favors, for example, the close mapping, that first computes the close mapping and then only can compute the argument mapping. And the result, for example, is this generalization there, where each time you have a phi, it simply says that it's a new variable. And as we can see, it's a pretty good generalization because it says that there's one clause where we have simply a base case where we have a 0 appearing. Then we have a clause where we have the empty lists. And these two are clauses with no bodies. And then we have the recursive case here, when we have the different literals that are anti-unified using the algorithm. So this is the first incarnation of the concept of predicate most specific generalization, with the use here of the quality function tau. We would like to explore other quality functions. We would also like to explore the handling of recursive calls, which are here simply abstracted by a lambda term, but we still need to better handle the recursive calls, because right now we simply consider them to be of quality 1 with one another. We would also like to minimize the number of different generalization variables to achieve even more specificity in the generalization, and then deriving a measure of distance among predicates based on the anti-unification. Thank you.
Thank you. So we have time for questions. Are there any questions?
A very quick question about applying this. Can you give us some idea of the size of the search space? I mean, if you're given two procedures and you want to find suitable mappings to see whether there is a generalization or a useful generalization of them, I mean, is it a huge search space to do that, or are there some good heuristics that will guide you to finding the right mappings?
Without the heuristic, you mean? So the whole search space?
Yeah, the whole the whole search space, and then with the heuristics.
The whole search space is, in fact, it's proportional to, you know, all the possible argument mappings. But this could be it's a mapping from the arguments of one predicate to the other, but it can be incomplete mappings. So it's combinatory on that level, because you should consider all the possible.
The ejected mappings of the arguments.
Yeah. And then for each of these, you could consider all the possible close mappings, which can be seen independently. So that actually explodes. I think it's I don't want to say to say a mistake here, but I think it's exponential. But with the heuristic, in the worst case, it's still exponential, because in the worst case, we have a matrix where all the qualities are at 1. But we have observed that that typically when the predicates use different functors, use pattern matching, use recursivity, well then there are lots of zeros that appear and the search space is heavily reduced and it becomes, in the example here for example, it's polynomial, it's really simply resolves. Yeah.
Other questions?
Thank you very much. A very quick question. Have you tried another measures or not? And do you have any idea of which kind of measures could be good to do that?
That's actually a good question. Here we have considered the tau value, which is the term size. We have really favored the term size of the results. But in one of our other works, we had, for example, favored the number of different literals that are generalized. So it's like we put a 1 everywhere rather than having different values. So this is an example that we have already tried. But as I said, we'd like to try other quality functions. And in fact, it's related to the third point here. We would like to define a quality function that actually allows to give a higher quality to those generalizations that have less different variables. And this is not captured at all for now, but that has, for example, if you have a generalization that uses xxx, this means that there's a data flow link at each occurrence of the x. And with the 5 function here, we achieve partly this, but we would like to investigate it further.
Okay.
Thank you
very much.
Okay. So, if you have more questions to Gonzague, you can ask them later. Okay, so it's time to go to the next.
Thank you.
Thank the speaker, of course.